second type of multiplication for vectors. You have multiplication where you put a dot, and you have a multiplication where you put an X, like old school timesing. This is the cross product. And the cross product of two vectors happens to be the length of one times the length of the other times sine of the angle in between times the vector n, where n is a unit vector perpendicular to both u and v. So the dot product is a scalar, it's just a number. But the cross product is a multiplication with vectors where you actually get another vector as an answer. Now, if you draw any two vectors in three-dimensional space, there's always going to be a perpendicular one out of those. But that perpendicular one either goes in this direction or in the opposite direction. So we have something called the right-hand rule. You might have done it in physics to tell which way or what direction the vector is going. So here's the idea of the right-hand rule. If you have two vectors, u and v, and I've got a little picture there, and I hired a very expensive hand model for this picture.
Is that you?
Thanks, Tanisha. What you do, if you have u cross v, you put your hand pointed on the vector u. And then you have, I could put my hand on the vector u either this way, or I could put my hand this way, with my thumb up or my thumb down. You have to be able to bend your other three fingers with your index finger still pointed on u to v. So here I am. So on this one, can you see that the only way that I could keep this pointed on there and bend my other fingers is if my thumb was pointed out from the smartboard? If I did this, there's no way without a lot of pain that I can bend these fingers back and match them up with u. So the right-hand rule says if I would do u cross v, I'd have to have my hand this way, bend my fingers this way. My thumb is now pointed outwards from the smartboard. That would be the direction of the unit vector n. If I did v cross here, there's my fingers nicely, look at that, little peace sign. Had to get my nails trimmed for that picture, polished and everything. If you did v cross u, okay, oh, this is another, I like this. I like this. Another way that you can visualize is to think about brushing your teeth. Okay? If right here, so here's u, here's v, and you're going u cross v, you're going from u cross v is going in this direction. U is first, then to v. If we drew an angle, it would be that in that direction. The other way that you can think about the cross product's direction, just like the right-hand rule, is think of a tube of toothpaste, and there's your lid. If you held your tube of toothpaste and grabbed your lid and turned it this way, would it loosen and come out, or would it tighten and go in? Now you have to imagine brushing teeth, right? Next time you grab your toothpaste, you want to loosen. If you turned it this way, it would loosen, and that lid would come off and outwards. Turning this way, that would loosen, right? That's the same as the right-hand rule. By loosening I had a wrench and a bolt, but I switched to toothpaste because most of you haven't worked with tools in your life. You'd be like, I have no idea. But with toothpaste, if you twist the lid counterclockwise, it's going to loosen and come out. If you twist it clockwise, it's going to tighten and go in. Same thing happens here if you did U cross V. You got to turn your hand upside down in order to be able to keep your index finger on V and turn it. This one has a weird angle for.
Like this. I don't see it.
That was easy to get like wood for a feet.
Ears.
Just rip for it.
Okay, ears, face, like nose.
Yeah, you have to look like on a diagonal.
You look at this, I don't get it.
It's like one of those like shadow puppets, you know?
Okay. Oh. Oh my god, yes. Oh my god,
Is it
yes.
Doberman? Oh, nice.
I see it.
I now can have like safety for my house on come because it's like, it's like, oh, it's a Doberman. I want to run away.
Molly does. See, Molly does a good enough job at that one.
So same thing, if you imagine vector V and vector U like this, and you did V cross U, that would be V cross U, the arrow would go that way. And if you think about taking your toothpaste and turning that way, it would tighten inwards. So that would be the direction of the vector. So U cross V and V cross U are not equal. They're very similar, but they're going to be in opposite directions. So one will be a vector coming out of the paper, perpendicular or orthogonal, and the other one will be pointed into the paper. And vectors of the same length, but going in opposite directions, are negative vectors of each other. So U cross V will always equal negative V cross U. Example 1. Angle between two vectors on a flat surface is 50 degrees. The length of U is 10. The length of V is 20. There we got a little diagram. Let's find the cross products U cross V. And I think it was supposed to say V cross U, but it said U cross V again. Is it fixed in yours, or does it say U cross V twice? Maybe we should just find it twice, be really thorough. Or maybe we just find it once and ignore the other one. So first, our formula. The cross product is the length of U times the length of V, sine of 50 degrees. And now, we have to think about, if we've drawn our diagram, because it says as seen in the diagram, U cross V is going to be going this way. Right hand rule, put your index finger on U and your other three fingers on V. Can you see that your thumb is pointing outwards from your paper? If you think about taking your toothpaste and turning it in that direction, your lid would come off. So when we write our answer, we also need to write a statement about which direction n is going. So the final answer, 153.209, with that vector n, and then saying where n is the direction outwards from your paper. And V cross U would be the same numbers, but it would be inwards. So was that too quick? Was everybody done? So some applications. First application of the cross product in 3 dimensions and 2 dimensions is that it can be used to find the area of a parallelogram. So if you had 2 vectors, u and v, you could replicate vector u up here and replicate vector v here, and you would make a parallelogram. In our old way of figuring out the area of a parallelogram, you would do the length of your base times your height. Algebraically, if you were given a parallelogram in the past, that's how you would find the area. What we're going to say is, well, if area is base times height, the base is the length of u, and my height, well, my height I could just write was sine of theta is height, opposite side over hypotenuse, and my hypotenuse is the length of my vector v. I can re-solve for h, and I find out that my area is just the length of u times the length of v times sine theta, and I'm like, hey, that's just my cross product. My cross product without the n vectors. So that means that the area of a parallelogram is just the length of the cross product. So if we took the vectors from example 1 and made them into a parallelogram, obviously this is not drawn to scale, but we know this length is 10, this length is 20, and this angle in between is 50 degrees. And the area of that parallelogram, we already figured out the cross product before was u cross v, 153.209, and n is a unit vector, so the length of our cross product is just going to be that coefficient in front of that unit vector, 153.209. Yes, a neat little application of the cross product. I'm trying to think, do I love it? I'm not sure, because if I had this information, I would probably, do you remember this formula? For area of a triangle, 1/2 AB sine theta. Can you see that if you join the opposites there, you would make exactly that triangle where you could use that formula? And if you do that to a parallelogram, you see that that would just cut it perfectly in half. So personally, I would probably use my old formulas and say I could find this triangle, and what would happen if I needed to find both of them? I would just need to double this. So the area of my parallelogram would be 2 of these, which would get rid of that half in front. And you still get the AB, same thing that we wrote here, AB sine theta showing up. It's just 2 of those triangles. But kind of neat that you can do cross product. And maybe this will be really helpful once we're trying to find, like, obviously this has happened to you often. You want to find areas of parallelograms in 3-dimensional space defined by 3-dimensional vectors. Right? Happened to me just the other day at the grocery store. But we could find areas of parallelograms in three-dimensional space. Easy. There is also a way to find the cross product just using the two column vectors. How is that for a formula you're going to have to memorize? Well, I'll show you a shortcut. But it's a kind of a crazy formula. The cross product of two vectors can be found with the following formula. But we're not going to use that formula. We're going to use some well, you can memorize the formula if you like. But I have two shortcuts for you that you may like better. Shortcut number 1 is very similar to finding the determinant of a 3 by 3 matrix. Okay? What we're going to do, we'll do it with the example, is you're going to take your first vector, and I put a blue box around it, and your second vector, I put a green box, and we're going to, maybe I should have taken away some of these arrows. Let's see if I can move some.
I have to write all of that?
Yeah, just wait. Okay. No, I gotta do this. Get this off. There we go. I'm gonna take away. Just wait. I'll let you start writing. Take away the red arrows temporarily. And take away the purple arrows temporarily. And what you can do is you can write ijk, ijk. Then with your first vector, the blue one, the I is 2, the j is -1, the k is 5. You write 2, -1, 5, 2, -1, 5. And with your green vector, you do the same thing. The I is -6, 3, and 8. -6, 3, and 8. Then, to find the cross product, first, go from I, j, and k and make diagonal lines and multiply the numbers on those diagonal lines. You don't have enough color? This is very much like matrix, like the determinant of a 3 by 3 matrix. Numbers in that direction will all be positive. Then draw 3 lines from I, j, and k in the negative direction. And it doesn't matter where your diagonal lines are. Like I did my first one with k, just because it's spaced out nicer. I could have drawn them with I, j, and k that way as well. What does matter is that in your I component, you take your purple I number, -8, and you subtract your red I number, which was 15. Now be careful, because the way that I drew the lines, you might be tempted to subtract the 6, but the 6 didn't match up with the I. Do the same thing with j and with k. And this is a little bit easier than memorizing the formula. This is method 1 is the formula. This is method 2 for finding the cross product with vectors. So everybody okay that I took the purple I, got -8? I took the red I, which was 15, I subtracted them. I took the purple J, which is right here, -30, the red J, which was 16, and I subtracted them. And then I went to K, the purple K ended up being 6, the red K was also 6, and I subtracted them. And so U cross V is -23, -46, 0. Yes.
So wait, can you use the key on the end or no?
Yes. So can you see that if I decided to use not this arrow, but this arrow here, I would still get 6, right? And then it's nice that way because they line up in the same order. But I didn't want to do it because I ran out of room on my diagram. But both are perfectly fine. You just need to make a diagonal. You could have used this as your I for the positive one. Can you see though that J, it doesn't match up for a positive one. This is the only positive J that gets 2 numbers. Okay, method 1. Okay, I'm sort of going from my least favorite method to my favorite method. Least favorite is the formula. Why don't I like the formula? Because it's hard, you have to memorize it, and it isn't easy to remember. Method 2 does the same thing as the formula. It's a little bit more systematic. It's kind of like matrix determinants for 3x3s, so a little bit easier to memorize. Method number 3 is using the determinants of 2x2 matrices. And it looks like this. Maybe find some space, I'm sorry. Do it off to the side. It's gonna, yeah, steal the page from the last time. Does this, it's,
Oh.
all right, are we ready?
No. Wait, where did I put it?
Go on the last page.
Go on the last page, there's some space.
Yeah.
Unless you drew pictures of my Doberman hand.
Well, you're gonna fit it on there.
I think this will be everybody's favorite method for the crosswalks. Okay. This is how it works. To find the first number, which is in I, stroke out all the I numbers and think of the remaining numbers as a little 2x2 matrix. And if you think of that little 2x2 matrix, what's the determinant of that 2x2 matrix? It would be -8 minus 15, and you'd get -23. You do this for each one, except when you get to the middle one. So now I want to find the middle one. I stroke out the middle numbers, which gives me a 2x2 matrix that's left. I'll call matrix B. If I find the determinant of matrix B, I get 46. But the middle one is always the negative of the determinant. So I is just the determinant of the remaining 2x2 matrix. J is the negative determinant of the 2x2 matrix. And then finally, the 1 in K is back to just the determinant. Stroke out the ones in the third, stroke out the ones that are the K, get a remaining 2x2 matrix, find the determinant of that remaining 2x2 matrix. Now I broke this up. The reason this is taking more space is because I wanted to give you a visual of each one separately. But when you go to do them, can I scroll down to here? Is that okay? Or not yet? Not yet? what I like about this method is you don't have to, the only thing you're rewriting is your two column vectors. You don't have to do the IJK, and write out the numbers twice. And you can do all of the mental math in your head quickly and easily. So the way that it would look in the end, this is what I had imagined. To write the negative 23, I just cover up these first two numbers. Find the determinant of what's left. Then to find the negative 46, I cover up those two numbers. Find the determinant, but make that one negative. And finally, cover up the third row, find the determinant.
Can you scroll up?
I can scroll up again.
So why did you only, sorry, I missed them, only put the negative outside for determinant B, but not for determinant?
So A and C are just the regular determinants. The rule is, for it to work in a shortcut, the middle one has to be negative. So it's just part of that shortcut. This method, I think, is the quickest for solving. So when we look at our next question here, consider the vectors 7, 3, 1, 3, 4, and x, and the cross product is 2, negative 11, and 19. And we want to find the value of x. If we set up our cross product, right? Set up our cross product. You see that if I cover these two, and I do the determinant, I would get 3x minus 4. That would be my coordinate for the first one. If I cover the second one, and I did the determinant but put a negative out in front, you would get 7x minus 3 with a negative out in front. And the last one, I would get 28 minus 9. So the last method is really nice for doing the mental math quickly. So I calculated my cross product using that last method. Now I need to solve for x. Well, now I know this is the answer. And even like the last one matches up perfectly, right? The k value here is 19, it's 19. That matched up perfectly. If these two are equal, then 3x minus 4 has to equal 2. And that happens when x is 2. Does that also work for the second one? When x is 2, does it equal negative 11? Yes. So that means we know that the x value has to equal 2. So again, just to recap, sometimes when you're writing notes, it's hard to visualize. What's the technique for finding, oh, we'll let everybody finish writing first, and then we'll recap that technique to see if you can visualize it. Okay? So, everybody ready? If if I want to find the cross product, I could use the formula, I could use the IJK method, or I could use the third method. Third method says ignore the first ones when you're writing the first one, and then do the determinant of the 2 by 2 matrix that's left. 3x minus 4. Which your formula says A2 B3 minus A3 B2 B3. Or no. A2 B3 minus B2 A3. But it's so much easier just to think of the determinant. For the second one, block out those two numbers. With the 2 by 2 matrix that's left, write the determinant, 7x minus 3, and add a negative in front. For the third one, block out the third row. Matrix that's left, do the determinant, 28 minus 9. And what's nice about that method is opposed to memorizing the formula, where the formula has 12 variables that are very similar in different places. This is a method that you just do the same thing all the time. You just have to remember that the middle one is negative. So now we can use the fact that we know that the cross product makes the area of a parallelogram. The length of the cross product makes the area of the parallelogram. And now that we have a technique to find the cross product with two vectors, okay? Thinking in 3 dimensions is hard. Can you imagine these two vectors in 3 dimensions? And then making a parallelogram with them? Anyways, to start off with, I'd like you to figure out the cross product on your own. I will put up the answer to the cross product in a second. So I would like you to calculate the cross product on your own. All right. How did you do? Did you get -7, 30, and 33? This is what we're finding. Then, the area of the parallelogram is just the length of U cross V, which is just the -7 squared, the 30 squared, and the -33 squared. And we get 45.144. This question also asked us to find the angle in between the two vectors.
Is there a matrix that's like split up into downtown? Yeah, not a
No.
good idea.
Wait, I have a question.
Mm-hmm. Are you sure?
Yeah, I do. Wait, there's like this one thing with like, I think it's an R with like 30 by 30. Oh, inverse. Oh, that's fine. Wait,
We can do the inverse with Gaussian Jordan.
like let's say you get the question right, and like that's a
Probably on the test. I'm going to ask you to do Gaussian Jordan in one of two ways, either by finding the inverse or by solving a 3 by 3 system with Gaussian Jordan. Probably more likely I'd do the 3 by 3 system. Gaussian Jordan.
oh,
And then your inverses, you could use your calculator. Okay, let's finish this question up and then we'll be done. Part B of this question says, to find the angle, now, in your cross product, there's sine theta. In your dot product, you have a formula with cos theta. When finding an angle, it is going to always be better to use your dot product for two reasons. One, your cross product is actually a vector, so it's a little bit awkward to work with a formula where you have vectors and vectors in the same formula. Two, since your cross product has sine of theta, when you solve for theta, you won't be able to tell if it's in quadrant 1 or in quadrant 2 for the angle between the two vectors. However, with the dot product, if cos of theta is positive, then you know you have an angle between 0 and 90 degrees. If cos of theta is negative, then you know that you have an angle between 90 and 180 degrees. So here's all the work. Found the dot product on its own, found the length of A, found the length of B. And the angle between them is going to be 140.621 degrees. That's where we'll stop for today.